In this first video about this new module called thermodynamics, we're going to introduce the topic. It's going to be a little bit of theory, but that may help us understand the main purpose of this subject. Thermodynamics is a discipline, a very broad discipline from physics that can be easily applied to chemistry, but its origins are back in the 18th century when people were interested in when the new steam engine was invented. They were interested in knowing how much fuel, how much charcoal do I need to burn to make this steam engine train move. They were interested in this conversion of heat and work. And therefore the name thermodynamics is the motion of heat. How much heat do I need to burn to make the engine move? How can I optimize this amount of energy? The application of all this old discipline into chemistry, it's called thermochemistry or chemical thermodynamics. And what we are going to study in this video is the first law. There is a zero law that we will not even talk about because we already understand thermal equilibrium, but the first law is what we also call conservation of energy. The principle of conservation of energy is assuming that the energy is constant regardless of its transfer. So the fundamental premise, the fundamental understanding of the first law is that when energy is transferred from one object to another, it has to appear either as work or heat. And the way we have to phrase this first law of thermodynamics is saying any change in energy in our system, let's call it the piston in the steam engine train, is because it has either gained or lost heat or gained or lost work. Okay, notice that heat again can be lost or gained, and work can be done or can be done on the system. We will talk about the signs of these two, and typically we will not be using this equation for practical problems, but it's important that we keep in mind that when we talk about conservation of energy, this is one of the formulations that can be used, that the change in energy of a system is because it has gained energy or lost energy. In what ways do that energy can come is either as heat or work. Let me give you an example in terms of molecular interpretation. So if we click here, we will go to this simulation. Notice in here that you're going to have some fuel that is going to react and hopefully move this piston. Here you have your reaction, and notice that as the molecules get some kinetic energy, they push this wall. You can imagine this could be a piston in an engine that could become work. Okay, so that's what we mean by work, and we could also think of heat. We can cool. If we cool down, notice that the gas is losing also energy. What is it that we want from this simulation? Let's go over through these questions. So right after the explosion, right after the chemical reaction, does the gas lose or does the gas lose or gains energy? Well, notice that there is a transfer from potential energy to kinetic energy. That is, the reactants had a lot of potential energy that gets released into kinetic energy, but it does not lose or gain energy. However, as soon as the gas starts pushing the piston, the gas will lose energy in form of what? In form of moving the piston, in form of what we call work. Okay. Notice that the molecules can get faster, but that does not mean that internal energy has increased. When there is a transfer from potential energy to kinetic energy, still the change in internal energy can still be zero. Just a transfer of the kinds of energy that the gas has. It will be a change of energy when the system, our piston, transfers energy in form of heat or work. This brings us to the understanding or the difference between energy, the internal energy. We will call internal energy something called state function. A state function is a property that a system possesses. Unlike heat or work, you cannot say that a system or your body has 2 joules of heat, because heat or work are called path functions, and that just means that it's energy in transfer. It's energy in transfer. So let's watch our words here, because when we talk about heat or work, it's not attributable to a system. It's when a system may gain or lose energy. Heat or work is energy in transfer. Unlike internal energy, that will just be, you can say a body has 10 joules of internal energy. It may gain internal energy in form of heat or work, but it will not have heat or work. Hopefully this distinction is clear. We will not go farther into definitions of state functions and path functions. There's a mathematical formulation for that, but you can always take physical chemistry to understand this farther.